right, let's go ahead and get started. Thanks everyone for coming to the virtual seminar this week. Our guest this week is Yare Ku from Harvard University. She is a PhD student there. Previously studied plate tectonics at National Taiwan University. And today she's going to be talking about potassium isotope anomalies in meteorites. So please take it away, Yare.
Thank you, Sean. Hi, everyone. Thanks for coming to the LPI seminar. In the next 40-ish minutes, I'll be talking about our result of potassium isotopes using a new model of ICP-MS with a collision cell. And this result suggests that potassium isotope anomalies observed in the meteorites are inherited from molecular clouds. So let's begin. The materials studied here are chondrites, the meteorites that contain spherical drops, which is pointed here with a yellow spot in the picture below. Chondrules abundance varies a lot from only a few volume percent to as much as 80 volume percent. And chondrites also contain fine-grained matrix, which generally disperse between the chondrules. And some chondrites are very important because they have refractory inclusions called CAI, as calcium aluminum rich inclusion, and CAIs are believed to be the oldest materials in the solar system. That's why chondrites are very important meteorite to study, because their parent bodies did not experience differentiation process. That means that the secrets of our solar system are preserved in those primitive materials. Chondrites can be classified into carbonaceous, ordinary, and antichondrites, for example. And they are classified with different petrological types from 1 to 6, as the little table shown there. From type 3 to 1 indicates an increasing aqueous alteration, while type 4 to 6 indicates increasing thermal metamorphism. And CI meteorites in particular are believed to be the solar initial composition. So in this talk, you might hear me mention CI meteorite for many times, because it represents the composition of our solar system. So a lot of reference and comparison are respect to CI. And in this study, we analyzed 15 ordinary chondrites, 4 antichondrites, and 11 carbonaceous chondrites obtained from multiple institutions around the world. So let's talk about potassium isotopes. Potassium has 2 stable isotopes, potassium-39 and potassium-41. The isotope ratio for potassium isotope is usually expressed in a delta notation, which is the 39 to 41 ratio of a sample respect to that ratio of a standard. All the potassium isotope composition in this talk will be shown in the delta 41 potassium notation. Potassium is important for planetary studies because it is a moderately volatile element with its depletion factor less than 5 in carbonaceous chondrite in relative to CI meteorite. Other elements like copper and zinc also classified as moderate volatile elements with a similar 50% condensation temperature, around from 700 to 1,000 Kelvin degree. Excuse me. Potassium isotope fractionations were believed to be direct results from the thermal events in the solar nebula or during the giant impact moon formation. 2 examples were shown here is from Humayun and Clinton study, and also one in Jacobson in 2016. Understand what mechanism causes potassium isotope fractionation could possibly tell us why volatile are depleted in many planetary bodies. So in this talk, that will be part of the content that we presented. In addition, that in this talk, we will also discuss other mechanism, mass-independent fractionation, and discuss if the possible potassium isotope variation could be related to the radiogenic calcium-41 decay. So I will go through our method and result to see if there's potassium isotope variation in meteorite. If not, then it will be the end of the talk. But if yes, then we will start discussing what mechanisms are most likely to explain the overall potassium isotope variation. And the discussions can be divided into mass-dependent and mass-independent fractionation. The mass-dependent fractionation means that the isotope fractionation is related to each isotope's mass. For example, if materials were being cooked or being heated, then the lighter isotope will evaporate faster and evaporate more than the heavier ones. This is why potassium isotope fractionation are important for us to understand the thermal event, if there's any. On the other hand, mass-independent fractionation mostly refers to the stellar origins that the isotope fractionation is not related to its mass. And many terms here will be used throughout today's talk, so I want to make it very clear here. Move to our analytical method. The first step we do is to gently crush rocks in order to make powder for dissolution. Then we use a mixture of hydrofluoric acid, hydrochloric acid, and nitric acid to dissolve the rock. And to check how representative our samples are, we dissolve multiple aliquots of the same powder, marked as A and B in the figure and in our paper. And the figure in the bottom middle shows that the powder we made are representative, and then the dissolution in column chemistry do not add additional uncertainty because the meteorite dissolved independently actually reproduce its isotope values. Step 2 is to run the bulk sample using a quadruple ICP-MS, which gives us the chemical composition of the sample. This step is important because we're able to learn the sample characteristic and further check for any potential contamination in the meteorite. And we will talk about this later. After making sure that nothing is wrong with the meteorite and get a very good sense about the potassium concentration, we will load the samples to the columns to extract the pure potassium. And then we run that potassium solutions to the multi-collector ICP-MS to get the isotope data. And the standard we use in this talk is the Merck Super Pure. So the multi-collector ICP-MS that we use is New Sapphire from New Company. It's a dual pass ICP-MS with a collision cell. So collision cell is important for measuring the potassium isotope because the collision cell enables removal of isobaric interference such as argon hydride, which can interfere the atomic ion of the same mass, for example, potassium and calcium. And with the collision cell, such interference can be removed by charge exchange reaction with hydrogen. So we're able to measure potassium in a high precision compared to the work in the past. Also, to ensure the quality of the data, we also measure a concentration mismatch standard. Here is an example shown on the bottom left figure. So we have a normal standard, and then we make a solution that has a different concentration standard. Then we run the sample to make sure that the tuning of the instrument can reproduce the result of this mismatch standard to acceptable, aka a good value. So here we show that a intensity mismatch of 14% standard solution gives us a potassium isotope value respect to the standard 0.017, which is less than uncertainty, means this instrument is well performed. For our data, the internal uncertainty can be evaluated by a within-run uncertainty, and it is the standard deviation divided by the numbers of sample standard brackets. That is normally 5 of them. So we reported internal uncertainty as 30 ppm. The external reproducibility includes instrumental day-to-day variability and uncertainties added through the column chemistry and dissolution process. As I mentioned before, the uncertainty for columns and dissolutions are negligible. So we consider our external reproducibility to be 27 ppm based on measurements of a single aliquot from different days. And many commonly used standards for potassium are also reported here in respect to super pure standard. I want to point out here that we're able to resolve the difference between the two potassium standards that are used in most of the potassium literature, the super pure and NIST 3141A. They're actually 0.047 per mil different. It sounds very close to each other, but it is very important to recognize this because all the previous study before this work assumed that two standards are the same. And since we're pursuing a higher precision measurement nowadays, this 0.047 per mil can really make difference. And as mentioned before, all samples were analyzed for elemental composition through quadruple ICP-MS to further check for contamination. And one CI value that was published in 2016 from our lab, that we have the same material left, and we analyzed the same sample, marked it as OGA1A and OGA1B here. We found that it is actually contaminated by 8% of terrestrial rocks. So much of the potassium in that sample is terrestrial contamination. And you can see that in the left figure, nearly 8% of contamination from Earth's average continental crust is derived from the rare earth element plus other minor elements. It is shown in the black dot line. And very clear that the sample is contaminated and has an enrichment in the light rare earth element. Additionally, the contaminated sample also has an Earth delta potassium 41 value that is shown in the right-hand side figure. The purple dot is the measurement from 2016, and it overlapped with other Earth samples. So now we look at the new OGA samples, OGA2 and OGA3 marked here. So those two samples were analyzing in this work and found no contamination. So here we present correct potassium isotope value for OGA meteorite to be minus 0.133 per mil respect to super pure. And this will be used as a CI meteorite values in this talk. And one thing to mention that A and B, 1, 2, 3 represent that samples were obtained from different institutes, and A and B represent that they're dissolved independently from the same powder source. Before moving on to our isotope result, I would like to explain how the group means are calculated. As mentioned, that a lot of meteorites were obtained from different institutions and were dissolved multiple times. And to minimize possible sample bias, the group means in corresponding to standard error as calculated are calculated based on the individual meteorite rather than the repeat. To be more clear, any meteorites that are analyzed more than once is considered as one single data point in the calculation. For instance, the top figure, the top table shows how we calculate the CV group means. That IN day was obtained from two different resources, marked as IN day 1, IN day 2, and IN day 1 was dissolved twice independently to make sure that IN day and Vigorano being weighted equally for calculated the CV group mean. We first calculated the mean for IN day 1 and IN day 2, where IN day 1 is the average value from 1A and 1B. Then we did the same for Vigorano. And lastly, the group mean for CV will be the average value for obtained from the IN day and Vigorano. We use this method across all group means to prevent the group means from heavily biased by one single meteorite. And in fact, that the two standard error, the uncertainty calculated in this way is more conservative, which covers a larger uncertainty. An example of CM meteorite are shown below. There's a small table. So as you can see that we take Murray, Mahai, and Murchison as only 3 input instead of 6 input, so that the two standard error is larger than if we just use all of the repeats to calculate the group means. This is why that uncertainty for the group means that plotted or presented in this talk are much larger than our reproducibility of 30 ppm. So on your left-hand side, we show that there are variations of potassium isotope in different meteorite groups. The y-axis is the potassium isotope composition. The more positive the value is, the heavier the isotope compositions are. And the x-axis is the calcium over potassium ratio, which represents a depletion factor, because calcium is a refractory element that the concentration of calcium doesn't change too much. You can replace calcium with aluminum, like a previous study from Bloom et al. Did. And looking at this figure, there is no clear correlations between potassium isotope and potassium depletion among all the meteorites. And this observation agrees with previous works too. So now let's further evaluate whether potassium isotope fractionation among the meteorite groups can be explained by evaporation condensation process under either kinetic or equilibrium conditions. So firstly, I'd like to talk about kinetic. The kinetic effect is usually under very low gas pressure, where the term Pi over P saturation is close to 0. And this process is considered to be one direction, and the isotopic fractionation for potassium is huge. But that fractionation magnitude can be suppressed by the surrounding gas pressure. That's why you see the kinetic effect times that 1 minus Pi over P saturation, which means that value can change depending on the surrounding gas. In a kinetic evaporation case, the residue is expected to be enriched in heavier potassium isotope because the lighter isotope tend to escape the system more easily than the heavier ones. So you would expect a trend showing that the most depleted sample would have the heaviest isotopic composition, like the little gray box in the bottom right, that you should see a positive correlation here. But we do not see that in our data on your left-hand side figure. On the other hand, for kinetic or non-equilibrium condensation case, that the condensate phase is expected to be lighter. And this is because the lighter isotopes have higher velocities that allow them to react more efficiently with the particle, then allowing condensation to happen. So the first condensed phase, or the material, will be the lightest in isotope. I have a green star showing that in the little gray box on your bottom right. And with more and more vapor condensed, the later phase, shown in red and blue stars, will have heavier isotope than the initial one. This is because the vapor reservoir is becoming isotopically heavier by constantly condensing out the light isotopes. And the condensed phase will eventually become equal to the starting composition when the potassium is completely condensed. So look at the figure. You might see a trend of kinetic condensation among carbonaceous chondrite. So the orange is CM meteorite, and CO is in blue, and pink is CV, and the CK is in the brown box. So some people might argue that, oh, there's a trend that is the same as the little gray box showing. However, this trend will require the starting material to be CM chondrite instead of CI chondrite. If that's true, then there are certainly more works need to be done to explain why the starting material is CM meteorite. And also, this trend cannot explain the ordinary and anesthetic chondrite. And actually, after consider the error bar for each carbonaceous group, the apparent correlation is just not that convincing anymore. So right now, we would say that neither kinetic evaporation nor kinetic condensation could explain the overall potassium isotope data. Now let's consider the equilibrium case. Equilibrium is where the Pi over P saturation is equal to 1. That means the rate of evaporation and then the rate of condensation is the same. So the isotopic composition of the condensed phase is expected to be heavier than the bulk system, no matter it's a evaporation residue or if it's a condensate. And that is something to do with the bonding of the solid and liquid phase compared to the atomic bonding in the gas phase. And the magnitude of equilibrium fractionation depends on the temperature and if there's any potassium-bearing minerals, such as plagioclase or feldspar. But the fractionation under equilibrium conditions is just so small, smaller than the analytical uncertainty right now, which again cannot explain the overall data that we see here. As other moderately volatile elements show that other elements were found to follow a mass-dependent fractionation, like zinc in the impacting experiment. We also compare our potassium data with zinc and copper isotope. If delta potassium-41 fractionation is caused by a thermal event and follow the mass-dependent fractionation, we should see clear correlations in potassium zinc and potassium copper. However, there's no correlation indicating that similar behaviors among them were not possible. And a previous study from Bloom et al. Also compared their data with zinc and copper and has the same conclusion as we do. So that means the main mechanism to explain potassium isotope variation is different from the copper and zinc. So our conclusion one is that single-stage thermal processing in the solar nebula cannot explain the overall delta potassium-41 variation observed in the meteorite. We also consider parent body process. like aqueous alteration. So no systematic correlations were found between potassium isotope and petrological types. In addition, many studies showed that mobility of potassium and other elements follow a sequence that I listed down there. To investigate if aqueous alteration has affected potassium in meteorite that we study, in your left-hand side, we plot rubidium versus potassium for chondrites in Earth. And you can see the constant ratio between potassium and rubidium suggests that no obvious alteration. Otherwise, we should see a highly variable potassium rubidium ratios, given that rubidium is more mobile than potassium. We also plot potassium isotope data to aluminum, chromium, iron, and nickel on your right-hand side. Aluminum and chromium are immobile, while iron and nickels might be mobile during low temperature alteration. All the plots here shows the same or very, very similar patterns, no matter potassium is compared to a mobile or immobile elements. So we conclude that no obvious alteration is observed to affect potassium isotope data, and using the large sample from multiple multiple institutes, we believe will minimize the local heterogeneity. Now let's discuss if mass-independent fractionation can explain our potassium data. As potassium-41 is primarily the result of radioactive calcium-41 decay, which means the variation of 41 to 39 potassium in meteorite could be traced back to a possible heterogeneous distribution of calcium-41. And short-lived isotope calcium-41 can be made through secondary thermal neutron capture, in situ radiation, and the S process. So here we want to know if the calcium-41 decay or any calcium-41 in the solar system could contribute to the potassium isotope variation or not. We choose the most calcium abundant material, that is CAI. First of all, we try to evaluate how much potassium-41 excess in the CAI are that excess are due to the calcium-41 decay after solar system form, and how much of that excess in CAI can actually contribute to the observed variation in potassium-41 to 39 ratio. And I promise this is the only slide that has math equations, and I hope that my explanation will make it easier. So first of all, that we calculate how much initial calcium-41 is in CAI using the literature data. Then we assume that all calcium-41 decay to potassium-41, which we mark it as potassium-41 star here. In order to compare to the delta notation, we divided potassium-41 to potassium-39 using stable 41 potassium plus the excess potassium-41 in the denominator. I hope so far so good. Then we use the 41 to 39 ratio in CAI divided by that ratio of a CAI-free matrix. This way, we know that CAI contributes 0.38 per mil, then more than the matrix component. We then choose two meteorites with highest and lowest CAI volume content, which is CV meteorites and ordinary chondrites. By a mass balance calculation, we found that the difference between CV and ordinary chondrites are too small to explain the 0.5 per mil difference. And because the bulk potassium concentration in the matrix in CAI are very different, if we had a chondrite fragment that contained 99% of the CAI, for example, it will only contribute less than 0.1 per mil. So our conclusion here is that potassium 41 from CAI to the total potassium 41 balance is not sufficient to explain potassium isotope variation, and that potassium 41 heterogeneity is likely presolar. Calcium 41 can form through neutron capture and as processed in stellar environment, and then could be ejected from massive star or by final explosion of supernova. After a lot of math from last slide, I'm just gonna use the cute emoji here on your right-hand side to explain the idea. When a massive star exploded to supernova, the neutron-rich isotopes are often ejected into the molecular cloud and become nebula materials, like extinct nuclide calcium-41, iodine-129, or neutron-rich isotopes like chromium-54 and nickel-64. Those isotopes are likely formed by nuclear reaction in the star before solar system form. And because calcium-41 has a very short half-life, the stellar wind or supernova ejection would possibly add abundant potassium-41 and very little calcium-41. So we plot our potassium data with epsilon 64 nickel and epsilon 54 chromium. The overall good correlations between potassium and nickel and potassium chromium suggest that the observed potassium isotope variation in meteorites could be the result of presolar nuclide anomaly, especially that nickel 64 is believed to relate to type 2 supernova shell explosion. And we also test, in our paper, we also tested that to see if this correlation can be reproduced by mixing multiple components, especially the one posed by Alexander in 2019. And then this model was used in a previous work by Bloom et al. To explain their potassium isotope data. So in this mixing model, Alexander used water CAI, a CI-like matrix, and fractionated chondrule, which have composition similar to the volatile depleted CI meteorite. In our case, there's no potassium in water and very little potassium in CAI. So Bloom et al. Used a matrix chondrule two-component mixing to explain their potassium data. When we tried to reproduce the result, we found that the CI material in their study is the contaminated sample in 2016, which means that CI matrix value is mistaken. And the chondrules calculated from Bloom et al. Also use a contaminated CI material as their starting material in the Rayleigh equation. So after replace the contaminated sample with the correct CI value, the potassium isotope variation cannot be the result of mixing CI-like matrix and chondrules under Rayleigh fractionation. And before and after results were shown in that table, in the table in the bottom right, that you can see the value actually change a lot after substituting with the correct value. And in our recent paper, we also try to test if this mixing model works by using the correct value and another value for a chondrule component. So we use a CI-like matrix and the CAI and the chondrule component that obtained from the average ordinary chondrites. The reason we use average ordinary chondrite to be the chondrule component is because ordinary chondrites contain up to 80 volume % of chondrules. So if there is one single value that can represent chondrule, we believe that will be best estimated by average the ordinary chondrites. As for CAI value in the paper, we use a calculated CAI value that is 0.382 excess in potassium 41 compared to metrics. So the matrix we use here is CI, so we just convert that value. We just use the CI value and then plus the calculated value to get a CAI delta 41 potassium value to be 0.25 in for the purpose of this mixing model. In fact, that given the super positive and anomalies CI value for epsilon 64 nickel and epsilon 54 chromium, the true value of CAI doesn't seem to affect the mixing region so much. As you can tell, that none of the sample located in that mixing area shown in gray in the figure on your bottom. If the estimated chondrule and CAI value do not convince you that we actually have the real chondrule and CAI sample measured in the past couple months, the small figures in the bottom left is the IND chondrule and metrics, and it shows that they're indistinguishable from the bulk IND, which is the red square. And on the right-hand side, we have chondrules from two ordinary chondrites, Elenovka and Saratov. They also show similar value to their metrics, despite that Elenovka actually has heavier composition than the average ordinary chondrites. We also measure 3 CAI from SBJ 101, and then the average CAI value is 0.163 with uncertainty of 0.15. And we want to point it out that this value is very close to the estimated value by assuming calcium 41 decay to potassium 41 in CAI. I think that's as cool, and then definitely more work need to confirm this. So we will keep everybody posted. For more information about this data, you can find our abstract number 2377 at the this year's LPSC. So if we use the real measurements of metrics and CAI and chondrules from different meteorites, we are not able to reproduce the data by mixing those components, because if you mix the chondrule and metrics from IND, you just get IND bulk samples. In addition, some people might argue that how about we just mix CI and ordinary chondrites to reproduce Earth and Einstein chondrite, which is shown in blue and yellow dots here. If you look up to the right-hand side figure, that we also plot potassium with big delta oxygen 17 isotope. You can see that the end member in the potassium nickel and potassium chromium figure are different from the potassium oxygen figure. So if mixing carbonaceous and ordinary chondrite to reproduce the error correlation that we see here, if that works, then we should expect that works for other isotopes as well. But we just don't see the same sequence of object in other diagrams. So we have two conclusions here. The first one is mixing of major chondrites component cannot explain the overall potassium isotope variation. And then the correlations of potassium 41 with nickel 64 and potassium 41 with chromium 54 such correlations can only be explained by a protosolar anomaly that is likely related to a type 2 supernova explosion. And what does that tell us about the protosolar molecular cloud? In order to have potassium-41 anomaly preserved in those meteorites, we propose a isotopically heterogeneous molecular cloud. So in this scenario, the isotope heterogeneity in the protosolar disk was inherited from the molecular cloud. And to have both anomalies preserved from moderate volatile elements like potassium and refractory elements like chromium and nickel, it can only be explained by a limited mixing of nucleosynthetic material. On the other hand, the depletion in moderate volatile elements, however, does not need to correlate with the isotope composition as long as the mixing in the disk only happen on the very local and small scale. And this also implies that the feeding zone for planets are relatively narrow and they do not disturb, well, and they're not disturbed by the later on giant planet migration. So, and we're also wondering, but we're thinking that any possible gaps that observed from the astrophysical observation, that a lot of gaps in the early protoplanetary disk could also be a barrier to prevent from the big scale radial mixing that supports that the mixing of planetary disk is very local and very limited. It will be great to see if future observations support this hypothesis, but just for now, that we conclude that potassium isotope anomaly are inherited from the isotopically heterogeneous protosolar molecular cloud. And that anomaly were preserved in the bulk primitive materials based on our potassium data. So we propose a new and correct potassium isotope value for the CI meteorite, and our samples are made from the large made from a large sample size and also obtained from multiple resources around the world, so that we are able to minimize any local heterogeneity. And we conclude that the single-stage nebula thermal processing cannot explain the nebula-wide potassium isotope variations. Then the coherent patterns between potassium isotope and elements with various mobility prove or supports that there's no observable aqueous alteration that could affect our measurements. The most likely interpretation for potassium, nickel, potassium chromium correlations in the bulk meteorites is likely the protosolar anomalies, and the data cannot be explained by mixing different components. And our potassium isotope anomalies support that now the protosolar anomalies are preserved for both refractory elements as well as moderate volatile elements in the primitive materials like chondrites. And those anomalies or those variations are likely inherited from the heterogeneous protosolar molecular clouds. With that, I will take questions. Thank you.
Thanks, Yurei. That was a great talk.
Thank you.
If anyone has any questions, feel free to ask them now or type them in the chat, and I will read them off.
Yeah, hi, this is Alan Treeman. I'm not sure I caught this, but do your observed heterogeneities in potassium isotopes correlate with this division between NC and CC meteorite sources? I saw it look like it did with the oxygen, but does it with the other elements also?
Yeah. I actually have a slide. We plotted potassium isotope with calcium 48, titanium 50, like all the isotopes that were thought to be protosolar anomaly.
Yeah.
And we can start from the bottom right. It's potassium, oxygen that we see, ordinary chondrite and carbonaceous chondrite that people argue is the two reservoir. That can also be seen in titanium. Those two different groups definitely exist in many of the plots over here. But then if you look at the sequence, that the Earth sometimes is in between CC and OC, but for neodymium and molybdenum, that Earth is actually on one side. So I will say our potassium data in general agree with those two distinct reservoir for carbonations in ordinary chondrites, but we're thinking there are definitely more nucleosynthetic component involved for this. And I hope this figure can answer the questions that you have.
Yeah, that's very clear. Do you have any sense of how many components are required by this? What have you got? 7 isotopes here, 6 different independent variables?
So definitely more than 2, but based on those, just based on the 6 figures, I do not have a clear answer for that. But I would guess, and I think at least 3 components will need to explain this overall distribution. Yeah,
They're very interesting. It's a complicated place, that early solar nebula.
Yes.
Do we have any other questions? Feel free.
Sean, I'll speak up if nobody else is going to pursue a question. This is David Crane. We have material heterogeneously distributed in the molecular cloud core, and I would use that phrase, molecular cloud core, as opposed to molecular cloud. And it infalls into the solar nebula, and some of that material is getting processed at fairly high temperatures. We have the production of CAI, we have the production of chondrules. So what is the carrier of that potassium isotopic signal? Is it surviving the processing of the materials that go into CAI and chondrules? Is it some other component that's lurking in the matrix? Do you have a sense of where to locate that carrier and what it might be?
Thank you, David. It's a very good question that we definitely think about that when we're doing this work. To answer the carrier for potassium anomaly, that we do not have a good idea for now. And since that we see a correlation between potassium to nickel and potassium to chromium, then the first thing we will think is what carries nickel and chromium might possibly carry potassium or carry calcium 41. And it's a tricky question and very important question, is because the precursor of potassium 41 is calcium 41. And calcium 41 is refractory and potassium is moderate volatile. So the time scale of the carrier, whether it's carried a refractory element or it's carried a moderate volatile element, is unknown. And I agree that is very important to really to understand what's going on. And if the carriers carry the potassium 41 anomaly, then I will think that somehow those carriers survive through those extreme local heating events for chondrule and CAI. But if the carriers actually carry calcium 41, then the other scenario could be argued. I do not have a good answer to that yet, and I think we need to do more research on really figure out what could be the most likely carrier to answer why the anomaly in potassium can be preserved.
Thank you.
Thank you.
We have a question in the chat. CAI is formed by various thermal processes, and many of them do not faithfully, excuse me, faithfully record isotopic heterogeneities in the early solar nebula. What types of CAIs did you use to test different models?
We didn't test model using CAI for the purpose of this work. So let me pull out the mixing. The CAI that we use to test on this mixing model is basically assume there is a universal value of CAI to use in this model. For example, that we measured SBJ 101 recently, and then it actually have a very close potassium isotope to what we calculated. And different CAI may have different potassium isotope, and then that may shift or change the mixing model that we just presented here. However, right now we only measure one CAI, and then I do not believe that different CAI will change the result of the mixing model that we just presented. But it will definitely be good to measure more CAI from different types. However, CAI is pretty hard to measure for potassium isotope because there are not many, the potassium concentration is really low in CAI, and then the calcium can cause some interference when we're measuring on the ICP. So I will say I can't guarantee you that we will measure more and then have the conclusion in the near future, but right now I can just say that I think different type of CAI wouldn't change our conclusion that mixing model doesn't explain potassium data. And I hope that answers the questions.
It does, thanks. Do we have any more questions from the audience or in the chat?
No.
If not. Well, thank you so much, Yari. That was a really great presentation. I really appreciate you coming
Very
out.
interesting.
Thank you everyone for coming, and please reach out to me if you're interested in the follow-up work or have more questions. My email is yku@g.harvard.edu, and you can probably find in many places. So please reach out to me. Yeah.
Okay. Thank you.
So we will not be having a seminar next week, so we will be sending out the announcement for the talk 2 weeks from now.
Hi, Kun.
Oh, hi, Kun.
I think he said hi and disappeared. It was a great talk, Yaya. Thank you.
Oh, thank you for